When the software is started up and the new project is created, the user meets the opening state of the interface. Geometry tab is active with only those functions available which are ready to use and others are inactivated, while a 1 square meter global grid with a visual representation of the origo and the coordinate palette showing the actual coordinates of the cursor is displayed on the modeling area. From this point, the user has 3 options to start a modeling function. The most straightforward way is to define the start and end point graphically using the mouse as the main input device. In this mode, pressing Shift can help sticking to vertical or horizontal directions or pre-specified directions in between. The default value between each step is 15 degrees. Using the graphical coordinate input, the cursor is only able to snap on certain division points of the main grid. These division points are placed in 1/10 of a meter by default, or, if pressing down the control button while moving the cursor, 1/100th of a meter. Each get function can be completed with either clicking the mouse or pressing the enter button. Default values of the cursor snap points and the angle constraints can be modified under model options of the settings. The second option to start a CAD function is by searching it through the so-called Smart Search and Command line, which is placed in the bottom left corner of the screen. The search line will offer the best match and the desired function can be started by pressing Enter. This search tool can be particularly useful for newcomers, as they may don't know where the button of a function is placed on the user interface. Still, they can find it by searching for the action they want to perform. The command line has further areas of usages as well, which we will cover later. The third option for starting any function is well suited for experienced users who are already well accommodated in AccessVM environment. Under keyboard shortcuts of the settings, each function of each tab of the software can be assigned with a hotkey. The applied assignments can be listed, saved into a file, and applied on another workstation by loading the saved file there. Hotkeys are displayed next to the name of the function in the pop-up info box, so for polyline function it is enough to press T on the keyboard. If coordinates are given manually instead of graphically, like we just did before, there are some things to consider. The first one is the difference between relative and global coordinate input. By default, relative coordinate input is enabled. That means inputs are measured from the insertion point, blue crossed on the screen, which place can be modified with the Insert button, but it always moves automatically to the last action point. So first I define a line quickly using relative coordinates for start and end points. Note that the 0, x, y, z coordinates means the insertion point itself. And then switching to global coordinate input, 0, x, y, z is the global origo. Okay, so with that out of the way, let's use some polar coordinate input to define the vectors of the beams of the frames. Cylindrical and spherical polar coordinate inputs are available, cylindrical being the default, so we need to input the radius by pressing R on the keyboard and giving a length, and the angle by pressing A and giving the pitch for the vector. To connect the two lines, we can use the extend lines to intersection CAD function, which will intersect pairs of consecutively selected lines for us. After we have applied cross sections to our geometry, the next step would be to add the hinged segments to the two sides of the beam. For this we will need to break the beam element into two segments, and first step to do this is to introduce an internal node onto the beam. There are many ways to do that, like the horizontal or vertical division, which intersects the model with the horizontal or vertical plane and inserts nodes at the intersections. A more straightforward way is to use the divide lines function. With this tool, we are able to insert internal nodes to an element based on several different methods, and we will use the divide by length option and use a 4 meter length as the length of the haunch segment. Another option is to insert the node manually. However, in case of a pitched member, defining the correct length can be tricky. So to measure the 4 meter distance from the corner of the pitched beam, the solution is to move the cursor along the reference line of the beam while holding down the shift button. And in this way the cursor will only move on the beam itself, and then by pressing the L button on the keyboard, length from the corner can easily be added to the insertion point of the node. So now we are ready to break apart the two lines. For this, we will use the break apart structural member from the edit menu, which function breaks apart a member at so-called breaking points. A breaking point is defined by different local x or z-axis directions, different material, cross-section or eccentricities, or like in our case, an inserted node. Haunches are defined as segments using variable cross-sections, with different cross-sections on its start and end points. Because the center of gravity differs along the haunch segment along the way, eccentricities on the start and end points has to be set properly to align the segment with the rest of the beam. However, we are working on a 2D frame. Lateral support effect of the secondary load-bearing system, like the purlins, are important. The supports they provide can automatically be taken into account during stability calculations using the O2 MCR method, and their effect is important during buckling analysis as well to get the proper forms of stability losses and their corresponding eigenvalues. First, we will insert the nodes where the purlins are positioned on the beam, and for this the divide lines function is used with a 1.8 meter uniform distance spacing. Next, we need to draw a perpendicular line from the gravity center of the beam to the upper flange, where the purlin support is located. Because of the pitch of the beam, this is not an easy task using graphical input, so we can use the perpendicular tool from the editing assistance functions, with which we can only draw perpendicular lines after we have defined the base vector. Length is given by pressing L and giving the length manually with the keyboard. The line element is turned into a rigid link before copying it along the beam using the spread by distance option, giving 1.8 meters for the spacing. Using the consecutive copy to place the element to the mid position of the haunch region, pressing down the shift while moving the cursor on the reference line of the beam can be used again to stick to the correct direction. For the other side of the frame, we will use a different, more general method to draw the perpendicular links for the connection of the purlin supports and the center line of the beam. We will use work planes. Work planes are user coordinate systems, making it easier to draw on oblique planes. By default, we are working in the global model space, defined by the main axis and the global origo. There are global work planes which are parallel with the global coordinate plane, so their position is defined by a single coordinate, useful when drawing stories of a building. We can create general work planes, which are defined by their names, of course, and then first by an origin, and then two vectors for the local x and y axis. When a work plane different from the global model space is being used, text on the coordinate palette will turn to red. Smart work planes follow the local system of a truss, beam, rib or domain. The origin is the first point of the element. Local x and y axes are parallel to the local x and y axes of the selected element. After the work plane is applied onto the beam one way or another, we can simply define the links by giving z-directional coordinate inputs, which will result perpendicular lines to the beam. Now we are adding connection points both for lower and upper flange. We turn them into connection elements and copying them all along the beam. Because the two lower flange support connection links are missing from the left beam, we will mirror them and copy them from the right. Pressing Shift while giving the mirror plane helps to stick to the vertical direction. As the supports are positioned in changing distances from each other on the columns, we need to use the horizontal division instead of the line division used on the beam before. During horizontal division, we need to input the distance from the insertion point where we want to intersect the members with the horizontal plane and create new nodes. The rest of the process of the creation of link connections works the same as in the case of the beams. After both column is ready, we can add the point supports to the ends of the connections, define the necessary loads and start the design process. Supports defined at their correct real-life positions can be recognized automatically and used by the AutoMCR method for stability design, and they are also essential to evaluate the correct backlink shapes during backlink analysis as well. In the next section of the presentation, plate editing functions will be used to convert the corner zone between the torsional restraints of the frame to see how local plate backlink shapes are formed in this region. As the column is handled as a single member yet, we will separate the upper part closing with the torsional restraint. Since the break-apart structural member will break the member into 5 separate members at every breakpoint, we will reassemble the lower part of the column. By selecting the corner region and using the Convert Beam into Shell model, we will convert the corner zone into a shell. Preferences for conversion of cross-section and beam arcs into polygons can be set in the parameter dialog. A shell model consists of shell elements created and connected according to the beam length and cross-section. Several modifications has to be performed to get the model working. Both flanges of the column will be elongated to meet the upper flange of the beam. For this, contour lines of the flanges will be extended to meet the plane of the upper flange. After selecting the beam's upper flange as the boundary plane, each line of the column's inner and outer flange needs to be clicked to be extended. Plate contours are completed using simple line elements where it connects to the beam's flanges. And so each rectangle can be turned into a steel domain, acting as the flange of the column one by one. As the web and the flanges of the beam and the haunch is not aligned yet with the outer flanges of the column, we will apply one last modification to position them properly. The drag and drop method will be used to move the boundary nodes of the webs and flanges into position. Clicking and dragging a node in AxisVM will activate the editing function, and by simply clicking on the correct position, the geometry and the corresponding domains will be modified accordingly. After we finished and performed the backlink analysis, we can get local plate backlink shapes, and based on the consideration of these shapes we can introduce further stiffening plates to the model. So the eigenvalue for this local backlink shape is around 3.5. Let's see what happens if we introduce some stiffeners to the model. We place a stiffener to the web of the beam and the haunch by copying the inner flanges of the column with the help of the Shift button to stick to the correct direction. And then we use the intersect plane with model function to separate the unnecessary hanging part of the stiffener. Using this function, we need to define a plane which will intersect with the domains of the stiffener and separate it from the upper part. Then we can delete the lower unnecessary part. We are also adding diagonal stiffeners to the corner box. First, we define the geometry for the 4 individual stiffeners using the slanted rectangle function. And then we define each as still domains. As a result of the added stiffeners, local buckling of the plates is focused on the haunch area with a higher 5.2 buckling eigenvalue. In the last phase of the presentation, we will show what are the peculiarities when the same frame is used in a 3D model, where the secondary load-bearing system is modeled with actual purlins instead of nodal supports, and we will see some model handling, selection and modification practices as well. The whole will have 4 frames in 10-meter distances, and positions of the columns are designated by the structural grid. Intersection points of the grid serves as snap points for the cursor as well when copying the frames consecutively. Purlins on the roof needs to be rotated into proper direction according to the pitch of the beam. If we have the exact angle value of the pitch at hand, rotation of the section with the beta value is the quickest solution. General solution to rotate members into position is by using references. Besides defining references with vectors, we can use the local axis of another member as a reference. Picking up the local z-axis of the beam as a reference can also be used to rotate the purlin into position. Now the purlin should be moved perpendicularly to the beam. So again, like in the case of the 2D frame, a smart workplane will be applied on the beam to match the workplane's z-axis to the beam's local z-axis. Lower flange of the purlin should sit on the top flange of the beam, so it needs to be moved in z direction on the new workplane by coordinate inputs. Using the normal transversal function and clicking on the 2 members, a line is added to connect the beam and the purlin. To define the connection between the beam and the purlin, a node-to-node link element will be used. The difference between the rigid element and the link element is that while the rigid element translates displacements and rotations rigidly between its start and end points, the link element has a third, intermediate node, which position and the translational conditions on this point can be set. The position of the connection point is represented by an arrow sign on the element, and it is positioned where the purlin and the beam flange meets each other. Purlins and link elements are copied along the beams, and the same process is being repeated on the columns. C purlins are added to the model, rotated and moved into correct position, connection defined using link elements, and then copied into the needed positions on the column. For the definition of lower flange supports, previously used smart workplane is fetched back and used to draw the connection line to the lower flange. A node is added in 1 meter distance from the start point, and then L-shaped supporting member is added, connecting the lower flange and the purlin. Then the composition of the connection and the supporting member is copied along the beams. In the middle frames, the composition also needs to be mirrored and copied to both sides of the beams. The same process is repeated on the columns as well to create the inner flange supports. The bracing system is defined using round bars with truss member types. In this case, by default editing settings, the software will automatically create a node at the intersection point of the two bracing. We want to handle each bracing member as one element during meshing, so this node needs to be removed. The remove node function can be used to remove intermediate nodes from a member. If we turn off the automatic intersection function on the lower icon bar, we can prevent the creation of these nodes. Right side of the hole is ready, so the next step would be to copy everything to the other side. The copy will involve quite a lot of entities from different types. Selecting them graphically is while an option. There are other more feasible ways to do it. One way is using the selection tool, which provides a wide variety to add or remove entities to or from a set of selection. Model parts, both software-generated logical parts and user-defined custom model parts, can be used to add a set of entities by simply selecting them from the tree structure. Applying a filter lets you specify filtering criteria to be used during selection. Using the checkboxes, certain types of entities can be added to the filter. Property filtering lets you apply further criteria like beam length, cross-section, material, surface thickness, reference, and many more options. Filter is now being applied in a way that it will select the purlins, both Z and C, the angle members, the link and rigid elements, and the truss bracings as well. Before continuing with the mirroring of the selected elements, let's use another option to make the same selection, which is by using the Search and Command Line tool. As discussed in the beginning of the presentation, the command line can not only be used to search and initiate commands, but it can also be used to make selections from the model entities. These selections can be based on a single or multiple criteria as well. Multiple criteria selections can even be used for selections based on the results after the analysis is performed, so we can make selections of members with specific cross-section, length or material, where a certain type of result component has its maximum value. To start a selection, the star sign has to be typed. Pressing Enter without specifying anything else will select everything in the model. If typing a minus sign after this, everything will be removed from the selection. So to perform the selection of entities which will be copied, a star sign is entered and first the rigid element is searched in the search bar. Since we are in multiple criteria mode, pressing Enter gives the option to add another entity, so we search for node-to-node links and press Enter again. Pressing Enter twice will perform the selection. We can add new entities to the selected ones by initiating a new selection, for sections this time. Typing section will offer every used section in the model, so we can search and choose from C, Z, angle and round cross sections and add them by pressing Enter twice again. Mirroring to the other side involves one useful setting, which is the mirroring of the local x-axis of the elements. This will grant that the purlins are aligned properly on the left beam as well. When it comes to modification of certain properties of an existing model, like section or load intensity changes, there is a function which can be effective both for the selection and the modification of the entities affected with changes. This function is the property editor. Property editor can be activated through the window menu and provides the fastest way to change properties of the selected nodes, elements or loads. After an entity is selected, every parameter of that entity is being listed in the property editor and then can be changed from the window. Selection based on a certain property can be extended to the whole model. To do this, click on a property and then the extend button. And this will find, for example, all the members having the same sections in the model, and changes can be applied on all of them at once. Most of the input boxes of the property editor, similarly to the coordinate palette, can handle basic mathematical operations. So for example, selecting all the nodes of the model, we can scale it up or down in each direction. Loads can also be selected and modified with the tool. They can be put into different load cases, change their directions, and of course change their intensities. So that covers the topic which we wanted to cover today, as we have finished with the modeling part of this whole. I hope it was useful and that you could learn some practices which you can take away from this presentation, and by that I thank you for your attention.